So here in lecture 8.4, we're going to introduce the controllability don't cares. Now in the previous lecture, we introduced the satisfiability don't cares that explain impossible patterns of inputs and outputs associated with individual wires in the network. But those turn out not to be don't care patterns. Those turn out not to be impossible patterns that I can actually use to optimize the two-level structure of something inside a node. Turns out there's a pretty easy recipe to go from the satisfiability don't cares to controllability don't cares that turn into real don't cares that we can actually use to optimize something. So let's go see how we actually find controllability don't cares.
We've finished describing what the satisfiability don't cares are. They belong to the wires inside the Boolean logic network. What we have left are the controllability and observability don't cares. And in this lecture, we're going to talk about the controllability don't cares. These are the first don't cares that are really things that you can use to actually compute something to simplify the inside of a logic node. The controllability don't cares actually specify patterns that cannot happen at the inputs to a network node. So how do you get the impossible patterns at the input to a node? So I've got a nice little example here. I've got a node that says f equals expression, then I got a bunch of nodes feeding it. So x1 equals ... x2 equals ... and then there's a vertical set of ... that says xn equals ... So I've got n Boolean network nodes feeding f as an expression, and I want to figure out what are the impossible patterns of f. There's a surprisingly simple computational recipe. So the first thing you do is you get all of the satisfiability don't cares on all of the wires input to this node in the Boolean logic network. So that's basically all of the xi nodes. And then you OR together all of those satisfiability don't cares. And remember, they're just Boolean functions. One of the great reasons for representing things as Boolean functions is that, as we're going to be able to see, we can do things like the union of all the patterns as a simple operation of ORing together the Boolean functions that represent those patterns. It's a really great thing about being able to do serious computational Boolean algebra. So you get the satisfiability don't cares on all the wires input to the node. So those are the satisfiability don't cares for the xi's. You OR them all together, and then you universally quantify away all the variables that are not used inside this node, because the xi's could be functions of many, many different variables, but if they do not appear in f, it's not relevant. We have to get rid of those variables, and universally quantifying them away is the right answer. And the result is a Boolean function, which would be called CDCF below, that's one for the impossible patterns of inputs to the node. So I can write this in a sort of a more mathematically precise form. The controllability don't care for f, right, is, well, what is it? It starts with the sum on all the input wires xi going into f of the satisfiability don't care on the wire. Now that sum sign, that big summation sign, is a Boolean OR. So I'm going to OR together the satisfiability don't cares for x1, x2, x3, ... xn. And then I'm going to universally quantify away all the variables that are just not used inside f. If there's a variable inside there that does not show up on the right-hand side of the f equation, I universally quantify it away. And the result will be a Boolean function that makes a 1 for patterns of inputs that are impossible for f. Why does this work? All right, so I'm showing the same diagram at the top, x1, x2, ... xn as inputs to the f node. And again, I've got the same formula. The controllability don't care function is the universal quantification over all variables not in f of the OR sum of all the satisfiability don't cares on the wires leading into f. Roughly speaking, why this works is that the satisfiability don't cares on the input wires explain all of the impossible patterns involving xi's that are input to the f node. So anything that's impossible that involves an xi, which is an input to the f expression, anything, okay, is possible. Anything that's connected to the f node, the satisfiability don't cares explain all the impossible patterns The OR operation on the Boolean functions representing the satisfiability don't cares is the union of all of these impossible patterns. It's sort of a beautiful, simple thing. If you can do computational Boolean algebra, you can do lots of set manipulations. This is one of them. The universal quantifier removes the variables not used by f, and it does so in the right way. We want patterns that are impossible for all values of the removed variables, and whenever you say, I want this result to be true for all of the things that I removed, you use the for all. You use the universal quantifier, the upside down A quantifier. And so that's why this stuff actually works. So let's go do a real one. So let's apply this computational scheme for controllability don't care extraction to the f node below. So I've got an x equals a plus b node and a y equals a plus ab node, and those things feed an f equals xc plus yd plus acd function. And there's also the primary inputs a, b, c, d going into the left and the output f going out the right. And so our formula says that the way this works is the controllability don't care for f is the universal quantification over all the variables not input to f of the OR sum of all of the satisfiability don't cares on the wires going into f. And so if we just sort of say, well, what are we looking at here? The input variables, the things that we have to look at for f are x and y, the output of some internal Boolean nodes, and the primary inputs a, c, d. So it looks like I need satisfiability don't cares for x, y, a, c, and d. What exactly are the variables not input to f? And the answer is b. B is the only variable that's not in f, right? A is in f, c is in f, d is in f, x is in f, y is in f. The only thing that's not in f, that's in all this other stuff, is b. We have to quantify out the b. So a good question here, because we haven't really addressed it so far, is what about the satisfiability don't cares on the primary inputs? You know, the things that don't have a network node in front of them, because in this case, A goes right straight into the F node, and C goes right straight into the F node, and D goes right straight into the F node. And so, you know, those are things that you know, conceivably should be important in this particular problem. But you can ignore, I'm going to put a star by this statement, it's important, you can ignore the satisfiability don't cares on the primary inputs, the A, C, and D, the wires that come in from the outside, because they're primary inputs. Why? What would the satisfiability don't care for A be? It would be A, the output, if you will. It's a wire, right? It's sort of like a null Boolean network node. It's the output, which is A, exclusive ORed with an expression for the thing that makes A, which in this case is A. So, right, so the satisfiability don't care for a wire named A is A exclusive OR A, which is 0. There is no impact on the OR, so you can just ignore it. So our recipe just got a little bit simpler. We still need to calculate the controllability don't care by quantifying away the variables not input to F and summing over all of the inputs that are the satisfiability don't cares, but the only things that matter are X and Y. And so I'm just going to put 2 check marks by the Boolean nodes. When you do this calculation, you just have to look at the stuff that came out of an internally computed node in the Boolean network. You only have to look at the arrows out of bubbles. You don't have to look at the external inputs. There's just nothing going on there. So we only have to OR together the satisfiability don't cares for X and Y, and then we have to quantify away the stuff that does not appear in F. So if we just do that, this is what we get. So again, I've got the network shown here, X equals A plus B node, Y equals AB node, feeding an F equals XC plus XD plus ACD node. I've got X and Y highlighted here just to sort of, we can sort of highlight the fact that that's what we're working on. Here's what happens. The controllability don't care for F is the universal quantification with respect to B of the following quantity. It's the satisfiability don't care for X, I'm going to put a check mark, which is X exclusive OR A plus B, ORed with the satisfiability don't care for Y, which is Y exclusive OR AB. So I'm going to put a check on the network node for that. if we do that, let's take the universal quantification and just make it happen so we can see what's going to happen. Well, we're going to get that expression x exclusive OR a plus b plus y exclusive OR with ab. We're going to cofactor that by setting b equal to 1. And then we're going to AND that with the same expression, x exclusive OR a plus b plus y exclusive OR ab, cofactored with respect to b equals 0. That will get us the universal quantification. And if we just do that Boolean algebra, we will get this result. I get a Boolean function, which I can write in any way I like, but I'm going to write it in this sum of products form. X bar a plus x bar y plus y bar a. Those are the impossible patterns for f. As long as I can represent this thing as a Boolean function and ask questions about what satisfies this Boolean function, and so, for example, BDDs would be beautiful for this, I can get everything I need to know about impossible patterns for the inputs to f. X bar a plus x bar y plus y bar a. That is a representation of a cover of the impossible patterns for f. So I've got it written down here again at the top, just for clarity. The controllability don't cares for f, which is a function of everything input to f, which is x and y and a and c and d, is the Boolean function x bar a plus x bar y plus y bar a. So let's just take one of those patterns, and I've just highlighted it here to be clear, to give a concrete example. Let's take the x bar y part of this Boolean expression. What that says, right, is that anytime x is a 0 and y is a 1, I think that's impossible. That's what this Boolean expression tells us. I think this makes sense. And if we just go down and look in the logic diagram, and I've drawn the same diagram, x is a plus b, y is ab, feeding f is xc plus yd plus acd. Let's just go look at that. We think that the controllability don't care tells us that x is 0 and y is 1 at the same time is impossible. So if we look at the network, if x is 0, then the output of the x node, which is an a plus b, is a 0. If the output of an OR gate is a 0, then A has to be a 0 and B has to be a 0. So I'm going to draw a little arrow like that. Okay? So if the output of X is a 0, then the inputs A and B have to be 0. Okay, so I'm just going to draw zeros on the A and B inputs. Well, if the A and B inputs are both 0, then when we trace this around to the Y node, if A and B are both 0, then the Y node has to be a 0. And what the impossible pattern told us was, if x is a 0, y cannot be a 1. Yes, correct. I'm going to write correct. Exclamation point. X, y, 0, 1 is impossible. If x is a 0, you cannot have y be a 1. We have just seen that. So x is 0 and y is 1 is impossible. We can use that as a don't care because that pattern cannot happen at the f node. Maybe we can simplify f using that pattern. Now, there's one more kind of controllability don't care that I really have to talk about. And those are things that are technically called external controllability don't cares. This is back to the very first slides in our don't care lecture. What if there really are just don't cares for the network input itself out at the level of the primary inputs? External patterns for the primary inputs themselves, A, B, C, D, that we just do not care what F does. What if those, like for example, they're just really impossible patterns of A, B, C, and D? How do I put that in the mix? Or said differently, what if I go back to the very simple, very traditional kinds of don't cares that we taught you back in your digital logic Carnot map days? What if one of those kinds of don't cares happens? So let's just be concrete. Let's say that B equals 1, C equals 1, D equals 1 cannot happen. Now what do I do? Well, I've got a little box over here that says don't care. B equals 1, C equals 1, D equals 1 at the network inputs. How do I compute the controllability don't care for F now? And the answer is pretty simple. You come up with a Boolean function that covers those external don't cares, okay, and you OR it in. And let me be very clear about what that means, in case I'm not. So here's the formula again for the controllability don't cares. The controllability don't cares for F are we quantify away B because those B variables do not appear in F, And we have the satisfiability don't care for x, that's x exclusive or a plus b. We OR in the satisfiability don't care for y, that's y XOR ab. And now we OR in a cover of the external don't cares, which is to say we create a Boolean function that's a 1 for these new patterns of don't cares that happen way back at the primary inputs. So that little red BCD, that's the external don't care. And just to be very clear, that BCD is a Boolean function that makes a 1 for the external don't care patterns. It is a cover of those don't cares. So just like everything else in this idea, when you want to represent a set of patterns of variables, you make a Boolean function that makes a 1 for the patterns you care about. So I need a Boolean function that makes a 1 when B is a 1 and C is a 1 and D is a 1. That's BCD. If I had a bunch of those kinds of patterns, right, I would have a bunch more terms and I'd just OR them all in. And if you do this, okay, if you do this OR and you do these exclusive ORs and you quantify away the B, you get the prior result, which was x bar A plus x bar Y plus Y bar A plus two new terms in the way I'm choosing to write this Boolean expression, A bar C dx plus A C dx bar. So there's some new patterns of things that can't happen because of the external don't cares. So the new controllability don't care function is the old stuff, x bar A plus x bar Y plus Y bar A plus two new terms, A bar C dx plus A C dx bar. Those are the new impossible things for F. And I've got the network again shown at the bottom, x equals A plus B node feeding the F node, y equals AB node feeding the F equals XC plus YD plus ACD. And I've got the little table of don't cares drawn at the left, B equals 1, C equals 1, D equals 1. And I've got one of these terms circled, A bar C dx. Okay, what does that say? A bar C dx says a couple of things. The first thing I'm going to tell you that it says is it says that A is 0 and X is 1. Right? That's the only way you can make this thing a 1. A is 0 and X is 1. Okay, so let's just go look in the logic network. If A is a 0 and X is a 1, then it must be the case that B is a 1. I'm putting a star by B is a 1. So I'm going to, over here, I'm going to put next to the sort of the don't care, I'm going to write B equals 1 because, you know, my pattern requires that B is 1. And A is a 0. I don't seem to care about that. But the rest of the pattern, the sort of the CD part of the pattern, says that C equals 1 and D equals 1. Because the only way to make A bar C dx 1 is A is 0, C is 1, D is 1, and X is 1. If A is 0 and X is 1, then B must be 0. But this pattern also says that C must be equal to 1 and D must be equal to 1. And oh, look, what have I discovered? I've discovered that this pattern is impossible. It's impossible because it touches and requires at the inputs of the overall network one of the impossible external patterns. So the new terms that you get in the controllability don't care, they light up. They turn on only when you're doing something impossible that involves an impossible pattern at the inputs, which in this case is BCD equals 1, 1, 1. So again, it all just works. So we now have the controllability don't cares. Controllability don't cares give impossible patterns at the input to node F. I can use them as don't cares to simplify things. They're impossible because of the network structure of the nodes feeding F. Controllability don't cares are can be computed mechanically from the satisfiability don't cares on wires input to F. There are internal local versions of the controllability don't cares. That was the first part of this lecture. You just compute those from the satisfiability don't cares on the wires that go into F. There are also these things called external global computability don't cares. Those are the don't care patterns at the network input. You can include those too. The result is controllability don't cares give patterns of things that are impossible, that cannot happen, that you can use as don't cares to simplify individual nodes. But it's important to know that the controllability don't cares are not all the don't cares available. Roughly speaking, the controllability don't cares are derived from the structures of nodes in front of node F. As we showed in the beginning part of this lecture, what also matters are the nodes in back of node F, the things between you and the output. So we need to go look at what happens with those kinds of don't cares in the next lecture.